Good morning, everyone. Welcome to another episode of Cloud Talk Show. Today is March 21st, 2021. Today is, and it's 11 o'clock in the morning, San Francisco time. And today we are going to demonstrate Mathematica code. I haven't been coding Mathematica for about 15 or 20 years. I coded Mathematica seriously for 10 years, mostly 1990s, starting from 1993 to about 2002. Then I have coded now and then, but not seriously. But before it was, several hours a day. So I wrote a lot of code. Now this code you are looking at is from 1998, okay, and apparently it still works. So let me show you some of the images I have. For example, I wrote this package. This is a transform 2D plot. Okay, this is the code. So this is the Mathematica code you are looking at. Now let me put, I have a bit cross size, so let me put this patch. It's actually easier for me to see this way. So today we are going to demonstrate Mathematica, okay, and maybe some tutorial. Maybe I'll do a beginner's tutorial to show you, you Python coders, Lisp coders, how it is. And if you have questions, ask me, okay? I love to see your comments and questions. We only have 5 people watching now. So I wrote this package. This is transform 2D plot, okay? Programmer's documentation. Hold on a second. Let me see, where is it? Okay, this is the one, okay? Transform 2D plot. Now let's magnify. And today's background image is, one of these images I created in Mathematica. I'm going to explain what they are. So for now, you can look at some pictures. Okay, let me show you some pictures. Pictures. Now these are transformation of a 2D plane. You begin with a grid. Okay, so let's see if I have, let me show you what they are. Okay, so this one is gallery. Okay, I need to open the documentation. Yeah, okay, so here is the kind of the most simple documentation. So I have to show you the grid, but basically you begin with a grid, rectangular grid or triangular grid. I don't have a triangular grid here, but I'm going to show you. So first of all, here is the code. Here's the code, begin package, and the documentation, inline string for documentation of each functions that gets exported. So in Mathematica, in many ways, it's just like other languages. You can import, export symbols. In fact, so Mathematica is my first language I learned for like 10 years, for like 7 years. So yeah, basically if you are not counting graphing calculators, that's actually my first language, HP28S. But anyway, Mathematica is basically my first language, and I code Mathematica for about 8 years. Then I started to learn Perl and Unix stuff. So that's around 1998. That's when I began to learn Perl, Unix shell, and Emacs, all those things. And it's a giant different experience, because Mathematica it so happens for me this is my first language, yet it is completely different from the industrial languages. So you are looking at, for example, the Mathematica code. You can see you have all these two-dimensional mathematical displays. So this is the package I wrote called transform 2D plot. So basically what it does is that you begin with a grid, rectangular grid or a triangular grid. Then you can apply a function, a vectored function that takes, a point, two numbers, okay, basically a point in a plane, then returns another vector, another, return two numbers. So you take a point and you put in the function basically move the point somewhere else. So you are looking at, beginning with a grid, you are looking at how the function transform the grid. For example, you can look at this one. It's interesting. So if you are wondering what kind of math is this subject, that would be vector calculus, but mostly complex analysis. Well, functions in complex plane, and actually, it doesn't even involve complex analysis, because when you do complex analysis, it usually involves derivatives and integrals. Gets complex. So this is actually pure geometry, and you don't need so much math to understand it. If you are a programmer, you can understand it. Basically, a function takes two numbers as input and output another two numbers, and these two numbers are considered as a point in the plane. So basically, the function moves the point to somewhere else. So, and this function, this set of functions I wrote, does the plot, transform a grid or rectangular grid to, by the function. So you can see there's also animations. Okay, so I think I'm going to just show you, random chat about Mathematica. So you can ask me any questions you want. Okay, you can ask me, type in the live chat any questions you want. For example, many of these functions you can see, about fish length, right? So this is kind of like a fish length. This is the actual function. Okay, so actually let me start to evaluate the code, so we can run the code in real time. So anyway, so here's the source code, page down. So for example, this function triangular grid that generates a triangular grid, I'll run it and I'll show you. Okay, this is the source code. Again, any questions or comment, type it. Okay, I'll get to it. So that's the code, and that's about it. That's the code for this package. Okay, okay, so select all. Oops, not that. Select all, and we are going to evaluate it. It's asking me do I want to evaluate init cells? No, because I'm going to evaluate everything. Okay, it's done. So you can see in Mathematica, every time you evaluate, the Mathematica. Okay, Mathematica has actually two parts. For example, in Java, you have Java. That's the command line Java program that actually runs the Java compile bytecode, and you have Java C that takes the source code and compile into bytecode. So for the Java language, you have several components. You have the compiler Java C, you have the Java runtime, which is Java, then JVM and so on. And for Python, Ruby, Perl, or JavaScript, basically you just have one binary blob, that compiles or interpret, and run a program. For Mathematica, the language, or you call it Wolfram language, it has primarily two components. One is the front end. Front end is what you see right here. So so these are the front end, and you have the kernel. So what is front end? Front end is what you see. Basically, you can think of it as a editor, or IDE, integrated development editor, IDE. So the front end is the editor or IDE. Then when you evaluate something, let me show you. Okay, So one, let's magnify. So let's say 3 plus 5. So you type this in front end, you press Shift Enter to evaluate, then you get 8. So so front end is kind of the editor. Then when you evaluate something, it sends the code into the kernel. Again, Mathematica has two components, the front end and the kernel. So the front end is, like the editor. You type something, you evaluate it, it sends the message via protocol to the kernel. The kernel does the computation, then send back the result, and the front end display it. So that's how it works. Front end and kernel, and in fact you can connect to multiple kernels. For example, you in the notebook you can see in this section, in this menu evaluation, you have kernel, default kernel, none or automatic or local kernel. You can choose a kernel, and if you buy Wolfram's grid computing, so basically your front end can connect to tens or hundreds of kernels, so it's a parallel computation. So front end and kernel, and front end is also the format of front end is a notebook. For example, you are looking at notebook. So okay, let me try to start to do some fun things. Okay, let me show you the functions. Let's see, and I'm going to look at comments. Okay, comment, guys. So let's try a function here. Polar grid and rectangular grid and triangular grid. Okay, let's try that. Okay, so you type question mark polar grid, that gives you the documentation for the polar grid. So let's try it. Polar grid, and it says R minimum, R max. So minimum, let's say 1, let's say max is 5, let's say step, let's say 0.2. Okay, let's see what happens. Oh, okay, so wait, you need them to be in a list. Okay, so you do need the second argument. Okay, let's just copy the thing then. I haven't used this. I haven't. This is coded in 1998, so basically I haven't touched it since like for 15 years. So R max is 5, then R step, let's say 0.1, and theta mean, theta max. Okay, theta mean, I don't know. Theta mean, let's say 10 degree, or is it degree, or I just want to get it run fast. Okay, 10, let's say 50. Theta step, let's say 1. Color function, generate a list of graphic primitives that represent a polar grid. The optional color function are used. Okay, color functions are optional, so let's run it. Error. What's going on? So does not have appropriate bounds. Let's say pi. This is bad. The first demonstration is screwed up. What's going on? Let's try rectangular grid. Okay, rectangular grid is simpler. Same thing. Okay, you need the same thing. Okay, x min, x max, x steps. So this is simpler. So let's just copy that. Copy, paste, and remove the quote. What's going on? That cannot be followed by. It's front end. Actually it's wow, look at that. Okay, it's trying to do something fancy. What's going on? So select that, Control Shift I to get input form, copy that, select all, paste. Why is it pasting this or this shit? This is copy, paste, magnify. Let's just type this in Emacs. 12025.1. Okay, 0.2. Okay, and repeat that, copy it back to Mathematica, paste, run it. Oh, it returns a list of graphics primitives. I know why. So you have to, what you have to do is graphics. There it is, finally. So rectangular grid, it just returns a bunch of basically graphics primitives. That means lines and lines basically. Then you have to wrap it around a graphics function. Then you have to show. Show is like print, except it's for graphics. Oh, thank you. So Kone gave me ISK $1,500 for hamburger. Thank you, Kone. So with all the knowledge you have of programming and math, have you considered building a crypto trading bot? No. Cryptocurrency is one of the things I want to study. I mean, it's one of the things I consider important. But I haven't, I began to study it seriously about 2 weeks ago, but I don't fully understand it yet. So first name, last name says, what are we doing today? So we are doing Mathematica demo. Okay, looks quite complicated to debug. Okay, so anyway, let's get back to Mathematica. So I wrote this package like 20 years ago. So let me show you. Okay, so actually copy that, Control Shift I. Okay, this is better. Now this you see the wait, did I miss a? You see the two different syntax here. So one is using the @ sign, while the other is fully nested brackets. In fact, they are equivalent to. Let me show you. Okay, let me talk about this. Now what I'm typing is called full form. Okay. In Lisp, it's known as meta expression. Yes. Wait. Symbolic expression and meta expression, right? So in Lisp, this is called symbolic. This is like Lisp sexp, while all these are meta syntax, meta form, meta expression in Lisp. Anyway, so if you look at all these three syntax are syntactically equivalent. They are completely equivalent. For example, evaluate that, you can see that's the output. Evaluate that's the same thing, output. Evaluate, they all the same. Now let me get rid of the, so you can compare. So all these three are exact syntactically equivalent. Now the difference is that basically some for typical programmers, you call them syntax shortcuts. So the at sign. So basically, all Mathematica expression has this form. So fx, for all f, g, something h x, something like so every Mathematica expression, this is the complete Mathematica syntax. Okay, it's just that brackets, symbols, alphanumeric symbols, brackets, numbers, and comma. That's it. Okay, whenever you see Mathematica source code, they can all be transformed to a syntactically equivalent form called full form, which is basically purely nested syntax like that. So this is one example. But Mathematica has a lot of shortcuts. For example, when you have a list like that, you can also write it like that. Okay, I'm digressing a lot, but let me show you something else. Okay, so for example, 1 plus 2, that's an expression, right? That's not a nested bracket. But if you want nested bracket, you can write plus 1 2. They are equivalent. Now, how do you know it's equivalent? Because you can type full form. Hold, okay, 1 plus 2. So here we have 1 plus 2. You want to hold it first. Hold it means do not evaluate it. Then you want to use the full form function that shows you the you see, it shows you the pure nested syntax. Anyway, I'm digressing. So I have showed and one more thing. Okay, one more thing. So when you see something like that, fx, that is equivalent to that. Okay, for any function. Now, one characteristics of Mathematica is very general. So for example, the at syntax is a prefix form. Whatever f may be, it may be a long complicated expression. X can also be a long complicated expression. Whenever you have an at sign, that's a prefix syntax for this pure bracket syntax. So anyway, let me get back to showing you the graphics. So this is a grid, and let's go back to show the polar grid. The polar grid. Okay, polar grid. Yeah, that's why it's wrong, because I know what is wrong, because I copied from this thing, and that has hidden. Let's type in Emacs, and it's better than just copy and paste. So polar grid, let's try that. Okay, that works. So now again, graphics and show. Okay, so there you have it. You have a polar grid. So you begin with this this grid that represents a plane. Then you apply a function to transform them. So all these are examples. So for example, here is kind of a fish lens, and this one, and this is more, this is distorted lens. Basically, you can think of it. It shows how how the function transforms the grid. Okay, so what else do I have? Then you have this one. So you see this function applied to a grid, or applied to a triangular grid, it looks like that, or applied to a polar grid, it looks like that. Then you have this kind of this function. This function, if you apply to a grid, it looks like that. If you apply to a hexagonal grid, it looks like that. and if you apply to a polar grid, it looks like that. So it kind of like, I don't know how you say it. It's kind of like shrink some parts and expand some parts. Okay, so that's the idea about this transform 2D, or which, any of these function. It's a vector value function. You can also think of it as a complex function. Complex function, a function that takes one complex number and returns one complex number. And in this example, this function, the function is here. Wait, so that's a function, and let me magnify. Okay, let's magnify. So here is a function, and this function is applied to a triangular grid. So you can see a triangular grid. So what does this function do? Basically, the further away the point is from the origin, the more rotation it does. So in the center, there's not much rotation, but when it gets further away, there's more rotation. So you can see some kind of these when you see I think a Japanese ghost film. There's, these days with your phone, you have what's called filters. You can apply filters to your face. So so I guess this is, there are similar function filter for this. It twists your face, so your face becomes, twisted. So that's what that is, and this is the same thing, the same function applied to part of the grid. And there are others. So it's pretty. So it's pretty. Okay, that's about that. Now I'm thinking. Now I can do a basic Mathematica tutorial, starting with like basics. How do you do loop? How do you do if? How do you declare variables? How do you things like that? We can do that, or we can do some random fancy demonstration, like which is more fun, but less instructive. Okay, so let me read the comments. So apparently ISK. Now, what is ISK? ISK is some Polish. Is it Netherlands or Poland or something? What? Brave browser, clear history. Okay. ISK. Icelandic. Oh, Icelandic corner. Thank you very much. So what shall we do today? Let me think for a bit, okay? So I'm still going, and I've been talking for 30 minutes already. Oh wow. So let's see my talk show, and what do I want to say about Mathematica? Let's see. This is too big. I'm thinking that, so you are looking at my Python tutorial, and so here is my Python tutorial, and I can go through the Python tutorial and show you how it is done in Mathematica. Why don't we do that? Yeah, I guess. Unless you have some questions, okay? So Python, you have tuple, you have a list, then you have tuple data structures, then you have sequence types, then you have dictionary, then you have how do you loop through dictionary or a list, then you have how do you write a package, and how do you write a function, and how do you write a class and object, and how do you write a module. Okay, it's we can go over that. It's pretty simple. Could you explain the basics while showing the fancy stuff? I could try. Okay, so let's let me so polar grid, rectangular grid. We haven't showed triangular grid. Okay, let me try GIANGU. Okay, triangular grid. But what is the syntax? Okay. Okay, so I hope to create a soft-like keys in Mathematica. I don't know. Okay, that generates a triangular grid. Yeah, so here is the output, but you need to. So these are graphics primitives. Let me tell you what they are. Okay, so first of all, you have a color. Then you have this expression. So this line is a function. Then it takes a list. Each element is a point, basically two numbers, x and y coordinates. So that represent the line from this point to this point. So this kind of thing, this is called a graphics primitive. It's like it's in like a JavaScript SVG, SVG, or in JavaScript canvas. You have similar things: circle, line, things. SVG, for example, SVG tutorial. You have SVG basics. You have how do you represent the line. So this is the syntax in SVG, how you represent the line. Then this is the syntax in SVG of how you represent a rectangle. So you say rectangle, x and y, width and height. So in the same way, in Mathematica, a line is represented this way. Now remember, like I said before, in Mathematica, every Mathematica expression has the form, like that. And all this, it's pure, nothing else. So that's why, you have that. So here is a list of graphics primitives. Now if you want to actually print this, so you have to say graphics. Okay, graphics. Then you have to say show. Show is like print, except it's for graphics. Okay, so if I do that, you got a triangular grid. Now let's increase that. Let's say 10. Okay, 10 doesn't work. So you want more triangles. 50. There you have it. 50. Let's try 30. Let's try 20. Okay, that's a nice one. So once you have a triangular grid, let's show you a function then. So we have a rectangular grid. Let's do some of these transform 2D plot. Yeah, let's do a demo. Okay, so let's show one of these. Yeah, actually the simplest is actually, okay, let's type it here. Transform 2D plot. Okay, in Mathematica, since okay, that's actually my function. Transform. Okay, transform 2D plot. How does it? What is the syntax? So first of all, you need a function. Then you need x min, y min. Okay, so that's simple. So x from x from 0 to 5, okay? Copy. Then y is also paste. Y is also from 0 to 5. Then what is a function? So you want to give a function. So okay, so let's say x and y. So this is a function that takes a vector xy and return xy, so it doesn't change anything. So let's plot it. Okay, so it begins with a grid, so nothing changes. So let's say 2 times y. Okay, so now let's change that, 2 times y. So you can see it kind of squash it. Now let's say y squared. Okay, it actually squashed more. So let's say here is x plus y. So this is kind of a shear. This transformation is called shear. It's part of linear algebra. Let's say sine y. Okay, sine y, x and sine y. Okay, so you got kind of like that. And now let's increase the plot range. Okay, I think you can kind of see a wave, more condensed, expanded, condensed, expanded, something like that. We can show it better by, oh no, okay, so let's try to show it better. Yeah, you kind of see it, but this is not so good. Let's see options. Plot points. Yeah, so you kind of see it. Okay, any questions? Hello everyone. Could you explain the basic? Okay, so let's do the basics. Okay, let's talk about how do you, the basics of Mathematica. Okay, the Mathematica language. Okay, let's begin here. So first of all, so here is you do addition. Here is you do 3 plus 3 times 2, for example. So arithmetics is similar. Now remember, Mathematica always returns symbolic result if the input are symbolic. Now if the input contains an approximate number, then it returns approximate number. So you could have a big number divided by something, okay, then it returns just that. And you can actually plus another random number divided by random number, then you got symbolic form. And if you want the result to be numerical, you can just use the n function, okay, which is, now the slash is a notation for postfix notation, like the Unix pipe. That's a slash. In other words, when you have let's say when you have that, okay, when you have g function applied on x and return value is feed to f, that is equivalent to these two forms are equivalent. So the slash is like a Unix pipe, and it works for any function. so it's very general. So in here, so that's why we use this //n. Otherwise, normally you can say this is how you do it. Yeah, if you want numerical results. So that's arithmetics, which is very common and not unusual from Python or anything. So let's see what else. Now, strings in Mathematica is just like other language. This is a string, okay, and you can also contain Unicode. So let me show you, okay. So Unicode, I love New York, for example. Okay, so here's a string. Go back to Mathematica, paste it, so you can have Unicode. And also one more thing, in Mathematica, so you can see this is a notebook, right? So let's save it. Let's save it. Let's save it. Let's see. Let's save it to desktop. Okay, Untitled. Save. Now I go to desktop. So here's my desktop. So here is the Untitled. It's that file. So if you open it in Emacs, it's plain text. This is what you see. So Mathematica file is all plain text. Now it's got this raw box. I don't like those things. The reason you have that is because error messages. But anyway, it should be easy to read. Okay, so let me get. Yeah, you see this pen box, tag box, grid box, style box, tag box, tooltip box. That's what are those? Those are kind of like formatting, like think of LaTeX. That's how you get this like table kind of like thing. So actually, let's get rid of that. Let's get rid of all these table like kind of thing. Okay, I don't want that. I don't want the style box and those boxes. Okay, I shouldn't delete that, but anyway. Oops. So wait. Okay, save again. Save. Now open this again in Emacs, so you can see now this is better, so you don't see those boxes. Now this is common in Mathematica. You use the parenthesis, then the asterisk sign. So the whole Mathematica is, again, Mathematica is like Lisp, right? It's a pure nested, purely nested syntax. So you can see here, you see this is the beginning of notebook, notebook. So then begin with a bracket. That bracket is basically the entire, the entire file. It's everything is purely nested thing. So that's the beginning. So this is the beginning. The thing above that is some kind of machine generated cache information. So it says this is a notebook, Wolfram notebook file. That's a comment, and the URL created by what product and cache ID. Then you have the internal cache information. All those are comment. So the actual notebook content is this line, beginning with the bracket. And if you match the bracket, it's basically the entire, you see, in Emacs you can jump to the end of bracket. That's the entire notebook. And until you reach the end, so that's here. That's the end of notebook. Then the rest of that is again cache information and some kind of temporary information. So everything is text, plain text. Okay, that's a Mathematica notebook, including graphics. Okay, so what about graphics? How does Mathematica represent, for example, this graphics. So if you open again in Emacs, you can see, let me magnify, okay. Let's see if it shows graphics somewhere. Yeah, okay, so it represents graphics by graphics primitives. Here it is, okay. Yeah, so this is the actual graphics. So you can see, but what is this? You know, graphics is very long. Wait, let's go back. Let's see transform 2D plot. Let's see the first graphics, okay? Polar grid. So back in Emacs, we go to the top, search for polar grid, okay? Search for that, search again, polar grid, show graphics again. You know, again you see this raw box kind of thing. I don't like that, okay? That means, okay, now go back to Mathematica. That means you are looking at, this is actually not plain text. I mean, it's plain text, but it's formatted. Let me show you. Control Shift I. Yeah, so this is better, okay? So this is actually like that. Return evaluated. Oh yeah, okay. Once you return, it shows, you know. So what does that mean? So basically what it means is that Mathematica automatically shows them, let me hold on a second, let me figure this out. Graphics cell convert to input form, cell convert to raw input form. Okay, that's what I like, raw input form. Okay, Shift Control R for raw input form. So now if I save the notebook, save and open it in Emacs again and magnify, go to the top, search for polar grid. So you can see it's much more simpler now. Before you are seeing a bunch of raw box, you know, those are typesetting things, you know, typesetting. So right now, so now you see the real, you know, the basic input, you know, text input, like a programming source code. Then you see this cell thing. The cell thing is actually, so back to Mathematica, the cell thing is actually that, you know, cell is kind of a unit of source code. So they, you know, each the source code is grouped by this unit, you know. So that's what the cells are. You can expand them or you can shrink them. Just like org-mod, you know, just like org-mod. You can also have titles. Let me show you, okay. Something title, okay, and select that. Then you go to style, format. You have headers, you know, second level heading and stuff. Style, yeah, style, title 1, okay. Then you have second level title, okay. So select that, cell, not cell, format, style, Alt 2 for subtitle. So once you have a title, you can see the title groups the entire notebook. So you can shrink, you know, or you can show just all the second level titles. The second level title doesn't group, but you can set it to group. So let's say this is Alt 3, the third level title. So you can see it automatically groups this thing. Then you can create another Okay, select that, Alt 3 something 5 plus 5. Okay, so what title is that? Format, style, chapter. Okay, title, subtitle, chapter. Yeah. What style is that? Alt 3. Yeah, okay, I made a mistake. There you go. So it's just like OGMAD, and also you can export the whole thing into LaTeX, LaTeX, or PDF. Okay, I haven't showed you some type settings, so I need to show some type setting in order to do so. Let's try this I showed last time. X from 0 to infinity. Okay, so 1 over x squared. Okay, so in fact, let's copy that again. We can evaluate this infinite expression encountered. Wait, does that let's say 1 to infinity. Okay, now you can select that and go to cell, convert to standard form. Okay, standard form, then it formats like that. You just press a key. Okay, so now let's save this. Okay, hold on a second. Let's save the notebook, go back to Emacs, close it, reopen it, magnify. Let's go to the bottom. Let's look at those summation. Okay, hold on a second. Let me do something else. Okay, let's select this. Let's make it raw input form. Okay, so raw input form is like just plain text. Evaluate that. Then okay, now save it, go back to Emacs, close, reopen, magnify, go to the bottom. Let me show you the corresponding part. So here, so you see this part, that's the raw input form. So you can see it's very simple. Sum 1 over x squared, x from 1 to infinity, and this input means input form. Then this cell change time is an internal recording of when did you modify that cell. Then you have a cell label. That's where you see the print, input 152, expression UUID. So that's all internal stuff. The most important thing you see is that part, and then you have a cell because the whole thing is a cell. So back to Mathematica. So that's what you see here. That corresponds to this part. Now you can see the output is formatted pi squared over 6. So now back to Emacs. Actually, we can display this side by side. So here is the output compared to that. So you can see, then you start to see this box thing, box data, fraction box, superscript box. What are those? Those are type setting things. So in LaTeX or TeX, you use backslash and curly braces, things like that. But in Mathematica, this is how you represent. For example, to represent a superscript, you do that. Okay. Now, what's this backslash bracket pi? That represent pi in a Greek font. Okay. So you see, this string is pi, and this string is 2, then you say superscript box that gets you pi over 2. Then you have you see the fraction box, that fraction box, so you got the whole thing. So this is how typesetting is represented in Mathematica. In fact, you can actually just copy this and it'll work. Okay, you can actually type this directly. So for example, let's try paste, enter. Oh, you have to, I forgot what you have to do, but you basically do I have, oh, you have to say box data. Maybe let's try enter. No, it's not formatted. I don't remember what you have to do, but basically you can actually type that in. But nobody does this, because if you want, there are much more simpler ways. But anyway, I'm just showing you the underneath, the how it represents typesetting in Mathematica. And it's plain text. So again, you can see everything is nested, purely nested brackets, syntax. Okay, so that's maybe that's it for today. But actually, we can continue to basics programming. So let's see comments. Hello, beautiful people. Hi. Hi. So how long have I been talking? So I've been talking for 58 minutes. Any questions about Mathematica? That's what we are focusing today. So let me just talk for 5 more minutes. Then yeah, let's talk for 5 more minutes. Then okay, so that's how you do. So we covered basic arithmetics. Where's my Firefox? So we covered how do you do string in Mathematica. Then join string. So something. Let's see if the plus sign works. I don't think so. Yeah, it doesn't work. So join string is join string, or join, maybe just join. Yeah, I think it's string join. Okay. Yeah. I haven't coded Mathematica for 20 years, but I still remember. The memory comes back. So string join, for example, A B C D E F. That works. I want to show you something else. There is another general syntax shortcut. That is, if you want to have a infix, there's a infix shortcut for any function. Okay, so in that form, for example, FAB. Okay, so here is a function, right? So FAB, that's a, F can be anything, A and B can be anything. That's a function. Now there is, for any function, there is also a infix notation for it, for a function that takes 2 arguments. You write it like this. Okay, this is general. This applies for any function f. So in the case of string join, we can do it. Let me show you. Now, if I remember correctly, I hope I did. I hope I was correct. Okay, enter. There it is. So again, we have talked about. So this is a generic shortcut syntax for the infix syntax for any function. We also talked about the prefix syntax, which is the @ sign, and we also talked about the postfix generic postfix syntax, which is the slash slash, which is equivalent to Unix pipe. Okay, what else? Let's see. So we have arithmetics. The assignment in Mathematica is basically the same like other language. Well, the basic ones at least. Then true and false. In Mathematica, true is this. Okay, true is a built-in symbol true. False is a built-in symbol false. So, and you have the n function that takes two any two expressions, and you also have the or function that takes any two expressions. Let's say, for example, okay, let's try end. Okay, 1 plus 3 equals to 5, and true. Is that true? False. Okay, 1 plus 2 equals to 4, and true. Yes, that's true. So and again, notice everything in Mathematica takes this form, function, brackets, then arguments, or nested. Okay, I think that's it for today, I think. So yeah, no comments today. Leo Cardo, you are late. Okay, Leo Cardo, where are you from? You've been here for a long time, watching my YouTube. Thank you. But I think you went on XR Discord once, but I never know or remember where you came from, in China or in Russia. Okay, that's it for today. Thank you guys for watching. Bye. So I'm going to do a lot Mathematica coding. Yeah, I need to update all my packages. I was actually surprised that my this package everything runs, and I was admiring my own code that's written 20 years ago. But there's a lot of changes. In 20 years, Mathematica has improved a lot. For example, a lot of functions I wrote today is not needed anymore. Okay, let me talk about this one. Okay, random color function generator. So this function, here's the source code. The first part is the inline documentation. Again, like I did 2 video within the past month. So there are 2 videos recently about Mathematica. So you should, if you're interested in Mathematica, you should go watch it. Okay. So 2 of them. So I said that Mathematica, the nature of Mathematica is like it's part of it is from Lisp, and part of it is from APL, the language APL, and another part is the pattern matching, the symbolic pattern matching. Mostly Stefan Wolfram, created. Then so here this function is interesting. Okay, so I have a function, random RGB color function generator. So what does it do? Let me show you. Okay, so it generates let's go back to my notebook. It generates where is my one thing I don't like about Windows is that everything is a window. It doesn't distinguish. For example, on the Mac, things are grouped into applications, not windows. So you have several applications. Then in each application, you have several windows. But on Microsoft Windows, everything is Windows. There's so I cannot press a key to switch to the next application. Instead of I press a key, it changes me to whatever. Wait, not that key. wait, do I still have it? I don't remember. I have, but anyway, the shortcut is Alt Escape. Yeah, Alt Escape. Let's see. Yeah, Alt Escape or Alt Shift Escape. That changes you to next window. So as you can see, as I change, I'm in Mathematica, then I'm in Task Manager, then in OBS, then in Firefox, then Mathematica again, Mathematica, then in Chrome, then Mathematica again. It doesn't group them, so that's one of the annoying. So now I have to. So let me show you this. Okay, I want to show you. Now I cannot find what's the other window. Yeah, I want to show you this function, random color generator. Okay, here is the definition, and basically it returns a function. Wait, did I run this code? Yes, I did. Why is it not returning a thing? What? I don't know. Let's run it again. Oh, I didn't run the code. So why don't we just copy the code? Paste it here. So now I run it. Now random RGB color generator. Okay, run it. So you see, so what it returns is, this is a function. Okay, this is a shortcut syntax notation for a function, or you can call it lambda. Okay, so this function takes no argument, but it returns a function, and the implementation of this function is a little bit advanced. For Lisp people, you can think of it as a macro. You need a macro. So what am I doing now? So what I'm going to explain. What is the point I'm going to say? So anyway, first of all, you are seeing a function that returns a function, functional programming. So functional programming is the main thing of Mathematica. It's the primary programming style of Mathematica. Basically you can think of Mathematica as a Lisp. Okay, it's not pure like Haskell. You can assign a variable easily. X equals to 5. Then x is 5. Then you can change the value easily. Okay, just like Lisp. So mostly you can think of Mathematica as a Lisp. So this function returns a function. Okay, how does this function work? Well, so how do you? How does this function work? Okay, so it returns a function. Now this function is the actual function that generates a random color taking one argument. Okay, so this function, for example, the output. So we are getting into functional programming. So anyway, so this function returns a function. Therefore, we can give it an argument. So let's say the argument is 0.5. Then it will return an actual color. Okay, so it's kind of brownish. Let's try it again. Okay, a different shade. Now let me show you something more fancy. Table just give you a list of things. Okay, so here n from 1 to 100. Okay, let's see. Okay, so you got a bunch of random functions. Okay, I wanted to show you something interesting about some I wanted to talk about Lisp macros. In fact, I want to tell you how Mathematica is actually a magnitude the Mathematica pattern matching, symbolic pattern matching is basically just list macros, but a magnitude more powerful. That is what I'm thinking of trying to explain, and that is in fact in this code. In this code you are looking at right here. Okay, um, but in order to do that, you know, I have to focus. I have to be really concentrated, or it'll take half an hour to explain every detail how it works. Let's skip it. Okay. Okay, that's it for today. Thank you guys for watching. Yeah, Windows doesn't have that. Windows tilde. No, Windows doesn't have. On a Mac, once you are in an application, there's a shortcut to switch to the next window of the same application. So you can cycle. For example, in Mathematica, I can cycle among all my Mathematica windows. But in Windows, you don't have that. So that's kind of annoying. Okay, bye guys.